deviations from ideal behavior. So remember, I said that all of these gas laws only apply to what are called ideal gases. But in extreme conditions, we start to see deviations from this behavior. So what are the two cases where we start to see significant deviation? So let's say we have low temperature. At very low temperatures, all of your gas particles move very slowly. So they move very slowly. So I've drawn little arrows because they're moving slowly. And because they kind of move slowly, when two gas particles come together, there starts to be somewhat significant attraction. So particles will start to attract. So can someone tell me what they think will happen to the pressure if the force of attraction becomes significant? Okay, remember, these particles are attracting each other, right? So that means they won't hit the walls as strongly because they're all clumped together. So what will happen to the pressure? So the pressure will decrease because the particles aren't colliding the wall as hard. Okay, what's the other problem? Let's say we have a high pressure, a very high pressure. This means that we've smushed all of these gas particles together. So now they're all confined. Okay, so now we have a bunch of gas particles and they're all colliding with each other and they're all in a very small space. So at this point, they start to repel each other, okay? The force of, the repelling force starts to become important because you guess, like, if you're trying to smush two things together, you can't, right? So, yeah, there's not enough space for all the particles, so they start repelling each other. So what do you think will happen to the pressure? So will it be higher or lower than ideal? So because all of these particles are repelling each other, they will be pushing on the walls harder, so the pressure will be higher than ideal. Great. So these two effects can be summarized using a coefficient called Z. So the ideality coefficient, I think it's called. So basically how it works is Z equals the volume. So the molar volume divided by the ideal volume. Okay, so this is the actual volume divided by the ideal volume. Okay, now we can look at a graph. So here we have Z on the y-axis, and on the x-axis we have pressure, I think. Okay. Yeah, I think that's right. So pressure. So at low pressure, we have ideal behavior. But then, as we start to increase the pressure, the particles will start to attract each other. So now the Z goes down. So, but then at some point, the pressure will be so great that the particles will start repelling each other, and then Z goes up a lot. So now, let's look at two different curves. So one curve is in black, and one curve is in red. I'm going to draw in red. So one of these curves belongs to H2O, and one of them belongs to helium gas. Now, water is a big molecule, so water is a lot bigger than helium. Okay? And water molecules attract each other. And helium molecules don't have any significant attraction. So with this information in mind, which curve do you think belongs to which molecule? So is the red line H2O or helium? Does this, oh, wait, why don't the colors show up on the screen? You can barely see the colors. So, yeah. Okay, there. So is the bolded line helium or water? Water vapor. Okay, great. So the red line is helium, right? Because as you can see, there is no attraction. So that means Z is always going up. Z is always going up, but also notice that helium molecules are very small. So that means that there's not going to be much repulsion since they can fit in a small space. So that means the slope is not very big. For water, we have a lot of attraction. So initially, Z will go down, but then it goes steeply up because the water molecules are so big, okay? So that they repel each other a lot when you start to bring them close together. And by the way, Z is called this compressibility factor. Okay? Okay, so now let's look at a slightly more complex equation. So here we have the van der Waals equation. So pressure plus n squared A divided by V squared times V minus MB equals nRT, okay? So what does this tell? Okay, so A and B are experimental constants that depend on the identity of the gas, okay? So let's look at B first, since B is a little easier to understand. So basically, B is a factor that depends on how big your molecules are. So B takes care of the fact that when we compress the gas a lot, the volume of the gas particles starts to become significant. Remember when we talked about kinetic molecular theory, we assumed that the volume of the gas particles was 0, but we can't assume that they're 0 for real gases. So we have to take that factor into account here, okay? Yeah. Okay, so notice so if we have a large value of B, this value will start to go down, okay? So this goes down, okay? And then since we assume that this can be a constant, so that means this has to rise. So that means the pressure will rise, okay? So, okay. So that means, okay, now let's look at A. So A kind of takes care of the idea of attraction, okay? So particles with more attraction will have higher values of A. How does this make sense? Well, as A increases, this part stays constant, and this part also stays constant. That means that this whole thing has to stay constant. And for this to be a constant, as A increases, pressure has to decrease. Okay? Now let's look at another an idea, okay? So let's consider sulfur hexafluoride. So maybe look something like that. So big gas. And what about hydrogen? So a little gas. So tell me which one of the so also the sulfur which one do you think has a larger value of B? So as you can see, the sulfur hexafluoride gas is much, much bigger. So that means we need a larger correction factor. We need a larger value of B, okay? And then H2 has a small value of B. So the van der Waals equation is pretty good, but it does exhibit some strange behavior. So we start to get these so when these two terms, when the V minus NB term and the whole P plus other stuff term, when those terms are about equal, you start to see some oscillations in behavior. You start to see some oscillations. So, and this obviously can't happen, right? Because as we increase the pressure, the volume should just decrease. We shouldn't expect any weird oscillations. So the van der Waals equation isn't perfect, but it's pretty good. And if you want an even more accurate equation, would be like the virial equation. But that's much more complicated. Okay. So does anyone have any questions? If not, then I think that we about ran out of time. So I think that's the end of the lesson. So